Right, so I'm going to do something a little bit different in this last lecture. We've spent the first three looking at language features and then doing a bit of hacking and demonstration. In this lecture, I'm not going to do any of that hacking and demonstration. I'm just going to tell you a little bit about what's going on inside Idris. Basically, an overview of how the type checking works, how elaboration works, things about the internals. Obviously, I can't give you full, complete details because this is only going to be an hour. But it is all written down, available. If you look at the Idris website, look at the publications page, you'll find some further details. So what I'm going to do is just give you an overview so that you get some idea of what's happening inside. The reason I'm telling you this, really, well, two reasons I'm telling you this. Firstly, if you want to become good at using any kind of programming language, it's really good to have a little bit of knowledge about what's going on inside, having a little bit of knowledge about the evaluation model, execution, how your programs are represented inside. Secondly, Idris is very much a research project. There's a lot of research still to do. We are still learning a lot about how to implement dependently typed programming languages, as well as a lot about how to program with them. So the more you know about the internals, the more chance you have of getting involved in that kind of thing. So if it's something that takes your interest, if you're interested in compiler design or code generation, all of these things, then what I'm going to say today will be a bit of an introduction for you to get used to what's going on inside Idris. Towards the end, I'm going to say a little bit about some possible directions you might want to go, some features that I'd like Idris to have, but I know I'm not going to have time to implement. And obviously having more people involved in the development effort would be fantastic from my point of view. So, what I'm going to talk about firstly is a little bit about what the core language of Idris is. I'm not going to give any real formal details. I just want to give you an overview. So you'll get an idea of what internal core programs look like. I'll say a bit about how we take Idris high-level programs and turn them into core language programs. And I'll say a little bit about the challenges involved in compiling dependent types above and beyond the challenges that you have in more conventional functional programming languages. So all of this code is available to browse. So it's open source, BSD licensed. You're very welcome to steal bits of it and fork it and do all kinds of other things with it. And all of that code is available on GitHub. I know quite a few of you have already made contributions, for which I thank you. But if more of you can, that's even better. Right. So let's start by talking about what the core language of Idris is. So I call this TT. I've always called it TT. There are a lot of implementations of type theory out there, calculus of inductive constructions, extended calculus of constructions, Jazilow's UTT. You always have to do some tweaks and fiddles to get these things being exactly the way you want it. So I've basically just given it a different name. I've called it TT. So it is a very simple core language. The only things that you can have in TT terms are variables, function applications, and binding forms. So binding forms could be lambdas or function bindings or let bindings, and pattern bindings, which I'll come to in a moment. And you can also have constants. So these are primitive constants, values of primitive types. You can also extend TT with some primitive functions. So there's, addition on integer primitives is something that's a way of extending TT. But as far as the type checker is concerned, they are just considered functions. They're functions that happen to have an internal implementation, but they're just considered functions. So the only thing that is allowed in TT programs, so we've got TT terms, which just has these variable applications and binders. TT programs only allow top-level data declarations and top-level function definitions. So function definitions consist of clauses in pattern matching clauses. So a left-hand side equals a right-hand side, just a set of those. That's all you have. So no where clauses, no type classes, none of that. And every term in a TT program has to be fully explicit. So remember, we've had implicit arguments to functions. We've had quantifying over a type variable or quantifying over a length. None of that is implicitly. None of that is allowed in TT. It's got to be completely explicit. This is something that once you've constructed a TT program, this is something that you could, in theory, feed to a separate external implementation of the language and have some independent system check that your program was okay. In fact, what really happens is there's a type checker which is just a very small kernel of Idris, just a few hundred lines of code. And when the high-level program has been translated into TT, it gets fed to this very small type checker, and the type checker checks that the term that you've actually constructed is something that is well typed. I've said here, about 500 lines, so that's the type checker and the evaluator. So I've written less chance of errors, and I actually thought probably more carefully about that particular line than any other line. So, what exactly do I even mean by errors? I guess what I'm saying here really is that if we work on the assumption that bugs per line of code is a constant rate for any given programmer, the fewer lines of code, the fewer bugs we're going to have in our type checker. I haven't actually changed the type checker for a very long time. I've made some minor changes to improve the efficiency, but I haven't changed anything in that kernel, and I really avoid, as far as possible, changing things in that kernel. So any feature I add to the high-level language has to be explainable in terms of the implementation of TT we already have. And if it isn't, well, something weird's happened. Something's gone wrong. So there's an obvious challenge here. We have TT is a very simple core language that we can easily type check, but it's not a language that you want to program in. And we're going to somehow have to get from our high-level Idris programs into these TT programs so that we can run the things. The only things we're going to run, the only things we're going to compile are TT programs. So I'll give you an example of how elaboration might work. So when I say elaboration, I'm basically talking about how you take the high-level program, turn it into the low-level representation. So that's what I mean by elaboration. I'll take a high-level Idris program, so a high-level data type, a high-level function, and I'll show you what happens to get from that when you go from that program into TT. So here's vectors. We've seen vectors a few times already. We're all intimately familiar with this data type. We've used it in quite a few of the exercises. Internally, so we can't have, this A is implicitly quantified over, this K is implicitly quantified over. We can't have an A and a K without them being bound somewhere. We have to have some explanation of what A and K are. So internally, what this looks like is, well, nil is for all A in type, so quantifying over A, there is a vector of A of length 0. And then for the cons case, for all A in type, for all K of type natural number, we can have an element and a vector of length K. So what we've done is change these implicit arguments to things that we're explicitly quantifying over. So as a programmer, you never want to have to do this because it's just going to get noisy. In fact, here's an example of how noisy it gets. And I picked a list with 2 elements here because any more and it wouldn't fit on one line. So the list of characters containing A and B, well, that's cons of, well, we better say to character, and we better say what the length of the remaining list is, because this length here tells us what the type of this list is. So this is going to be a vector char of suck of 0. And then this one is also a character. It's got length 0, so the length has got smaller. And then we've got the value, and then we've got the tail of the list. And this tail also has to say what the element type is. Otherwise, this won't type check. So there is a question. Yes, David.
What about vet in itself? Does that not also get a definition?
Yes, it did, but it's just the same as this. So there's nothing funny going on with vector because there's no implicit arguments. It actually does just look the same. So that yes.
So you have a top-level definition just like nil.
Yeah. I was just trying to keep the noise down on the slide. I mean, there's already, we haven't even got very far in elaboration. There's already a lot of noise in what this. Well, it's not really noise. It's kind of important. But as far as you or I are concerned, it's noise. As far as the machine is concerned, this is important to explaining why this is a valid program. So that's the definition of vectors in TT. So what about programs? Well, this program, this pairwise addition of 2 vectors. So we saw this back at the beginning. So we've got an implicit A, we've got an implicit N, and we've also got this type class argument. So we'll have to do something about type classes as well, because type classes aren't allowed in TT. So this vadd, it looks like a function of 2 arguments. Actually, there's 3 more arguments. There's also A, there's N, and then there's this type class. So as a sketch of what the elaborator is doing when it sees this function, first thing it'll do is it'll identify that there are implicit arguments there. So it'll notice A and N, it'll think, okay, I don't know what A and N are. I'd better quantify over them. So remember the rule is that if there's a lowercase, an identifier that begins with a lowercase letter that is not bound, then you'll add implicit quantification. We've also turned this type class argument into an explicit data argument. So type classes can just be represented as dictionaries of functions, so a record containing the definitions of functions. That's exactly what's happened here. So the numeric type class just turned into an actual concrete argument. So in the definition of VAdd, on the left-hand side, I've added these three arguments. So the first two, well, I don't know what they are yet, so I'll just put an underscore to say, well, we're going to have to figure out what this is. For the type class, we just give it a name. And then for all the nils and conses, we have to expand those to have the implicit slots for their implicit arguments. So we've got nil of underscore, and we've got cons of underscore xx's. Plus is also so plus is defined for anything numeric. So we're going to have to fill in its type class argument. So we've got a lot of holes we have to fill in basically. Before we can actually check this as a TT program, we're going to have to work out what goes in all of these holes. Now, the way we fill these in is through a unification algorithm. So while we're elaborating the program, we'll look at each subterm and we'll use a unification procedure to work out what these things have to be in order for the program to type check. So for each of these underscores, there is only one choice that will make this program okay. So in this case, in the nil case, the only thing that's going to work in the type position is an A. For the nil case, the only thing that's going to work for a length is a 0. We get this from the definition of nil. We know that nil needs to be a vector of length 0, so unification will fill that in for us. And in the cons case, we know that it has to be a successor, and we know that these vectors have to be one smaller. So there's a k here that's smaller than the successor of k. And then we know that this type class is the thing we have to propagate through for addition. And then for the recursive call to vector add, we have to feed in the type, the length, and the class again. So if you read any texts on type theory, programming in type theory, this is basically the kind of programs you have to write. You have to be fully explicit about everything, and obviously this is not something you want real programmers to have to do, because you spend most of your time figuring out exactly what these arguments are. In fact, when I was first working on implementing Idris, basically started by implementing the core type theory, and I was having to write programs of this form. And as you can probably imagine, it was very easy to make mistakes in propagating things through. So it's vital to have that unification procedure to fill it in for you. So we still haven't quite finished, because if you look at these clauses, so VAdd A, 0, C, nil A, we've got an A and a C here that don't appear to have any meaning. So in order to be able to type check this, we're going to have to know what the types of A and C are. So the final step is to make the pattern bindings explicit. So as well as lambda for all let bindings, we have these pattern bindings that essentially they just give a context in which to type check pattern matching terms. So while we're elaborating the left-hand side of a pattern match, when we see a variable, we'll just make a note of it and think, well, okay, we're going to have to work out what the type of that is. Now these clauses, these two clauses, are rather a lot longer than they were when we started. But these clauses are something that we could reasonably feed into some external procedure and get type checked. So there's a bit more to do after this. So we're going to have to turn this into a case tree so we can actually run the thing. But you can just think of this as the final definition. We've written a pattern matching definition, which we can then run. So is that all making sense so far? Anyone have any questions on how that works? I mean, you're all reassured that you don't have to write things like this. And you all believe that this is something that is possible to check by a machine. It's nice that these are checkable by a machine which is much smaller than the language itself. But, it's just a tiny percentage of the code of the whole system is in checking these. So that's just an ordinary top-level pattern matching function, plus a type class, plus a couple of implicit arguments. So in general, Idris programs could contain quite a few high-level constructs that you don't have in TT. So we could have where clauses, You can have type classes. Do notation. We've got with, the with rule. So we've got, introducing dependent pattern matching. We've got case structures. Pattern matching let, which you may not have seen, or you may have independently discovered with it. So pattern matching let is just where you say, let some pattern equal something else, and the variables will get bound, just like in a Haskell pattern matching let. Also, types are left locally implicit in quite a lot of places. So we need top-level type declarations on our functions, but we don't really want to put type declarations on every binding. So we don't want to have to say, let x of type something equals something else. We don't want to have necessarily to have a type annotation everywhere. So locally, types might be implicit. So on a lambda binding, for example, a type might be implicit. And as far as possible, we want those to be inferred by the machine. So these are all things we have to fill in when we start running the programs in TT. So we don't want the high-level language to be as expressive as possible, but we also want to keep something that's actually translatable into this low-level representation. So everything we add, we have to think about how it turns into this low-level representation. So before I say anything about how we do that, I'll just make a little observation, which is, I've certainly had experience writing programs in Coq and writing programs in Agda and Idris. And something I'd observe, not necessarily everyone shares this opinion, but I find that writing pattern matching definitions is a nice, convenient abstraction for humans to be able to write programs and for humans to be able to read programs. Come to that. So you'd rather write your pairwise vector addition in a pattern matching style than in a sort of tactic style where you say inspect x's and then make a recursive, check the induction hypothesis to make it a recursive call. On the other hand, tactics are still a convenient abstraction for something. So tactics are found to be a convenient abstraction for building programs by refinement, and particularly for building proofs by refinement. So if I have if I have something that says x equals y and I need to make an x and I've got a y, then it's much easier, I find, to be able to apply a rewriting tactic than it is to actually write the program that does the rewriting, just because it does the work for me. So in particular, tactics are a convenient abstraction for explaining programming to a machine. So it's I think easier to explain to a machine how to build a program by running a few tactics in sequence than it is to explain to a machine exactly what it means to be a program. So as a typical Coq user, you'll be a typical Coq user, I suppose, as a human normally, but there's no reason why. I don't mean as opposed to a dog or as opposed to a cat. I mean as opposed to a computer. But there is no reason why. There's no reason why, just because you have tactics, they have to be something that's operated by a human. So it's, in fact, this is something I think in general is it's well worth writing your program so that the interface is something that's just as easy to be used by a machine as it is to be used by another human, because then you can start writing programs that generate programs. So the idea, therefore, is that humans write high-level programs by pattern matching, and then the machine translates that into a TT program by using tactics to build those programs by refinement. So a high-level program is, in some sense, a very high-level tactic that explains how to construct a TT program. So this high-level program structure, every high-level construct is given an interpretation as a tactic sequence. Then we check that tactic sequence has built a program that is, when we erase it, is equivalent to the one we fed in. So we go from, the elaboration procedure is therefore to go from an Idris term to a TT term by using tactics, by constantly refining the program according to its structure, and then, as a sanity check, to take the resulting TT term, erase it back to the original program, and see if we get back to where we started. Right. So now I thought a lot about how I was going to describe this elaboration process to you. I thought, well, should I should I give you exactly the details of what's in the code, or should I give you a sketchy overview, or should I go somewhere in between? I decided in the end it would be better to just give you an overview of what's going on rather than exactly what all of the details and complications are. So it's not. This is just a kind of disclaimer to say that what I'm about to show you is not directly equivalent to what's in the code, but you will recognize it in the code when you see it. So, for example, a monad might have lots more things in it, or a function might take a couple of extra arguments just because, realistic programs always have more complications that the idealized programs that we present in talks and papers can pretend they don't have. So this is more to show you the structure of elaboration than to show you exactly the details of how it works. So what we have is, we've encapsulated everything in a monad called elab. So this elab monad, it's a state monad. All it has is a proof state, and everything we do updates that proof state. There's a little bit for managing error as well. So if you think about it in terms of effects, like we were yesterday, it's basically got state and exception as effects. So what's in the state? Well, there's a proof term, a current proof term. So as we're building a program by refinement, as we're taking a high-level program and turning it into TT, we'll have an incomplete proof term as we're going. And hopefully, by the time we get to the end of the refinement, we will have a complete proof term that doesn't have any gaps, anything missing. So the proof term I've noted here says it includes holes. So what exactly are holes? Well, holes are just incomplete parts of the proof term, and the way we've represented holes is just by another form of binder. So you've got lambda bindings, let bindings, pattern bindings, and hole bindings. So, query x.scope. And there's nothing particularly special about them except for the fact that you can't evaluate them, so you can't run them. They won't. Well, if the result of elaboration is a program that contains holes in it, well, that will fail the type checker. So I don't know if any of you have ever have come across the error this week of incomplete term. Yeah, a couple of people nodding. So you'll see incomplete term, and then there's a blob, kind of an underscore that says what's missing. Well, the reason you get that error message is because there is something that the elaborator couldn't figure out because unification didn't have enough information to fill it in, and that basically means there is still a hole that couldn't be solved. Did you work that out for yourself when you got that? Or yeah, sorry, you.
Was the distinction between holes and question mark thing?
Right, so the question mark in user code is a sort of global meta variable. So what happens when a question mark turns up is the elaborator says, okay, what type do I need to fill this in? It then makes a top-level function definition, applies to everything in scope, and then solving a meta variable is just basically defining that function. So the distinction really is a presentational one. I found it better not to give users too easy access to holes while elaborating, but it is still a nice idea to give users access to holes if you have incomplete programs. So basically all that happens is anytime you see a question mark, it's assumed to be a hole that can't be filled in, and it's just lifted out to a top-level definition. Yeah. Right, so we've got a current proof term, which is just like an ordinary program, except it might have these holes in it. We also have unsolved unification problems. So this is, as we're refining a program, we might do during type checking and so on. Does this thing have the same type as this thing? We might have, the type we're expecting and the type we've got. And it often happens that fails, but it only fails because there isn't enough information. So imagine you're trying to unify y with x plus y. Now, obviously that's wrong, because y and x plus y are different things. But it could be that as you go further in your elaboration, you establish that x equals 0. And as soon as you've established that x equals 0, that unification problem that was previously broken is now solvable. So what we do is we keep track of the unsolved unification problems. If another problem gets solved, every time we solve a unification problem, we basically quickly run through the problems we've already got and see if we can make further progress. So ideally, this collection of unification problems, by the time we get to the end, is going to be empty. So when you see an error reported, that means we finished doing elaboration, and the set of unification problems was not empty. So some unification problems fail very quickly. So if it's trying to unify successor with 0, then it doesn't bother postponing that, because successor is never going to unify with 0. But anything that might be solvable with further information gets added to this list of unsolved unification problems. So we also have the current focus, the subgoal in focus. So let's imagine you're writing a program which is simply f applied to 2 arguments. So what will we do? We'll make an application of f. We'll invent some subgoal for the first argument. We'll invent some subgoal for the second argument, and we'll solve them in turn. So we keep a list of the subgoals still to be solved, and we keep track of which one is next. So we'll just work through them in order. I noticed the 2 AGDA programmers in the corner are giggling to each other. I wonder if they've proved bottom again. No, they deny everything? No, fair enough. And finally, we'll have a global context. So once you define something, once you've defined a name, that gets added to some global context, and your proof can refer to it later on. So functions get defined in turn, so it's defined before you use one after the other, and then this global context contains all the things you've defined so far. So I'm going to show you some slightly simplified type signatures of things that are going on inside the elaborator. Something that I find very useful to do in any language implementation is to distinguish non-type check terms from type check terms. Raw is something which hasn't been type checked yet. It might contain placeholders. It does contain sort of expanded implicit arguments, but it hasn't been checked or elaborated yet. A term is something which has been type checked. So if type checking succeeds, then a raw will turn into a term. And I find it very useful because terms and types are in the same syntactic class. So we can represent them both the same way. But I do find it very useful to have type as a synonym, because then there's just something you can see the meaning of a function. On the other hand, you can understand that these two are the same thing. So there's a few primitive operations that we'll find useful in our elaborator monad. So if we've got a raw term, then it would be very useful to be able to check whether that raw term is type correct in the current context. So this checks in the context of the current whole in focus. So we've got a whole in focus, which means we're going to have an environment of all the things that are in scope at that point in the term. And it means we have access to all the global definitions. So this function will check that this is well typed, and if it is, it'll return us its term and its type. So this is very often useful if you're checking just a name or some simple term. We'll also need to normalize things occasionally. So if we've defined, if we have some complicated type, we might want to reduce it to normal form to check it in a particular form. So if you're checking that something really is a function type, for example, we will need to normalize it. That just takes a term and returns a term. So I should mention this because I know at least David has been bitten by this. I spell normalization with an S, not a Z. The reason I do that is not because S is the British English spelling. This is a common myth. If you look in the Oxford English Dictionary, they're both correct. The only reason I spell it with an S rather than a Z is because S is definitively wrong in American English. That's all. It's pathetic, really, isn't it? It's to cause trouble for the Americans. Nicola.
Do you have something less aggressive than normal?
Yeah, I do actually. I have a head normal form function as well. Which actually is normally the better thing to do, because normalization can go a very long way. Can take a long time. The earlier implementations did a lot of normalization. The current implementation tries very hard not to normalize anything unless it really has to, because that can, as I'm sure you'll understand, get very slow, and it can also break sharing if you're not very careful. So we avoid normalizing if we possibly can. So unification comes up a lot. So we have. I haven't given you a very helpful type here. This, as I say, I've simplified this. I've actually oversimplified unify. So unify takes two terms. Checks whether they can be made the same in the current context. So like if we're unifying x plus y and y, then that's going to fail. But if we establish from some other unification if we then unify x and 0. That can be made to succeed, provided that we make x 0. So what unify will do is solve those any meta variables that it can. So the question.
Yeah, temporarily assume that x will be 0 and then leave it as a whole or something.
Can you temporarily assume something? That doesn't happen, I suppose. Well, the trouble is to do that. If you're unify x plus y and y, you're saying can we say, well, this could only work if x is 0, so let's guess that. I think in general that is going to possibly lead to trouble because you're going to have to look at the definition of other functions. So you're kind of trying to work backwards from the definition of the function to what the inputs must be. So in general, I think that is something you can't do. But there might be some situations where just to increase the power of finding implicit arguments, it might be useful. But no, I don't do that. Unification, as I've implemented, is actually, it's pretty dumb. It's just check the normal forms of things, see if they are the same if you solve some meta variables. So the only things you're allowed to fill in, the only things unification is allowed to fill in is holes. So it can't just invent a new value for a variable. An earlier version had the amusing bug that if you filled in a value for a variable which wasn't going to unify, it changed it for you. So it fixed your programs for you. I decided that was in some ways helpful, but in one way helpful, but in every other way a bad idea. So actually, this is a sort of higher level version of what we really have. So this is the version that takes two terms, unifies, and then solves variables. Actually, unification just returns a list of the solutions, which it then feeds on to the other unification problems in the context. So it's also there's all kinds of things in this elab monad. I won't tell you everything that's in it, but there's all kinds of things you might want to do, like find out what the current goal type is, find out what the current proof term is, find out what holes are still to be solved. So you've got to get the local environment, so return the names and types of things that we have available. So this, for example, might be useful. I showed you the trivial tactic, didn't I? I think the trivial tactic is something that just searches the context for something that matches what we want. So the trivial tactic works by calling getenv and then just trying everything in the list that comes out. It does that because it's quicker than normalizing all of the types to see if they match, because you just do it. It's done exactly the same thing. So we've got an elaboration monad with all of these operations that do stuff to the proof state. So a subset of those operations are tactics. So tactics, you played a little bit with tactics, and we've done intros and rewrite and refine. So internally, everything is built by tactics. It's just a function that updates the proof state. It might update the term. It might solve a sub-goal. So changing focus is something it might do. Building a term in some way, so adding a binding of some form. So the few we've got here, focus just moves to another sub-goal. Claim says, well, this introduces a new sub-goal. It introduces a goal with this name and this raw type. So if you're doing a function application, you'll just claim names for each of the arguments and their types and work through them. For all, that introduces a for all binding. Exact says, right, I've finished now. I've worked out what this term is going to be, and this is what it is. Apply is a slightly more complex tactic. It's not quite a primitive tactic. It uses some of the other ones. So that takes a function and a list of arguments and solves the current sub-goal with a list of the function applied to its arguments. And naturally, you can running one tactic on its own is not going to be that useful. So you want to be able to combine them in various ways. The easiest way is just by sequencing them with do notation. So like a proof script, claim X, then apply F, then apply X. But also some combinations are useful. So sometimes a little bit of proof search is handy, like type class resolution, for example. You might try a few different things while you're searching for the thing that fills in your type class. So this try tactic applies one tactic, and if that doesn't work, it applies the second tactic. And if that doesn't work, well, that's no use. We give up. Also, try all. This is a more generalized version of this. And try all just applies every tactic in its list, and exactly one has to succeed. So if more than one succeeds, that's a failure. If none of them succeed, that's a failure. And what this is used for is if you have overloaded names, it just firstly it tries to prune the overloaded names by looking at their types. And if there's still a couple left, it says, well, okay, let's just see what happens. And if more than one of them works, then you have an error. So that's how type-directed overloading works. So effectively, what we've got now is an elaboration monad that we can use to write proof scripts. Now, I used to call this elab an embedded DSL for building programs. And the main reason I don't call it an embedded DSL for building programs is I submitted the paper describing this to the JFP, and one of the referees very reasonably said, aren't DSLs usually usable for other problems besides the one you implemented it for? And I thought, well, it's debatable whether this is an embedded DSL that is usable for things that aren't implementing Idris programs. I guess it could be. You could change the syntax, but it's really only something for constructing TT programs. So I guess I'll stop calling it an embedded DSL. But I very much had embedded DSLs in mind when I made it, because, like I said the other day, when everything, when you're only tooling a hammer, everything looks like a nail. So everything looks like an embedded DSL to me. So I'll give you a couple of examples of how this looks in practice. I won't go through the whole language, but the paper I was referring to, so it's now been revised and it's still being refereed, but it's something you can download and look at. So if you've got a function f applied to some arguments, how are we going to do that? Well, we need to type check f. We need to know that f is well typed, and all the time, by the way, every step of this process, we know the type we're looking for. So it's type directed. We have a top level type declaration. So we always know we're looking for a particular type. So we'll type check f in the context of the current Go type, and that will yield types for every one of the arguments. So f itself will have a function type. If it doesn't have a function type, this isn't going to work. So for every argument that comes out, tie I, so I is just representing an index here, we'll invent a name for it, and we'll run the tactic that basically introduces a sub-goal for that name. So now we've got a load of n's, so we can apply f to them. We've got n's that are well typed. We know they're well typed because we invented the types that the function said it wanted. So that's easy. We can now safely apply f to n's. We might actually get some unification errors here, but by filling in the n's, we'll hopefully resolve them. So if for some reason there is a relationship between the types of the arguments, it might be that you need the value of one before you can reasonably write down the type of the other. So it is possible that there'll be unification errors at this stage. This is why we have a list of unification problems that we hang on to, that we might solve later. And then for every argument that is not a placeholder, so something that's not an underscore, something we don't expect to infer, we'll focus on the corresponding n, and then we'll elaborate the argument. Now, if we're still left with meta variables at this stage, if we're still left with placeholders, well, we're going to have to hope that they're filled in somewhere else, that some other part of the process can fill those in. If we don't have enough information, well, that's where you're going to get this incomplete term error. So does that process seem reasonable for type checking a function application? Now, when you've got a set of tactics that basically allow you to construct programs, it makes this elaboration process really easy, because it sounds like, well, clearly to type check an application, you type check the function, then you type the argument. What could be simpler? But so yeah, I've mentioned this complication. Elaborating an argument could affect the type of other arguments. So applying So applying vector cons, the length argument is going to affect the type of the tail argument. So we've got an append function, say, just as an example. So 3 implicit arguments, a, n, and m. So here we are, a, n, and m. And if we're going to build an application of append to 2 arguments, so this is the high-level Idris application, well, we're going to have to claim types for each of the arguments. So we'll invent types for a, n, and m. We'll invent types for x's and y's. So I've actually, these vector n, we're actually going to have to call the elaborator recursively for these. But I didn't want to write the whole thing down because it would have been far too much. So we'll claim types for x's and y's. And then we can apply this function plus plus to all of the arguments. So we're going to have to work out what a, n, m, x's, and y's are. But for now, we can build the application and see if we can make progress. So next thing we do, a, n, and m, well, they're placeholder arguments. They're implicit arguments. We'll have to fill them in. So next thing we do is just focus on x's and recursively elaborate this argument. Then we'll focus on y's and recursively elaborate the other argument. And with any luck, the process of elaborating this argument and this argument will be enough information for us to get a, n, and m. Of course it will be, because this is going to give us 0 for n, and this is going to give us int for a and 2 for m, just during the process of elaborating it. So that's, well, this is a specific example, but it's not far off what the code for a function elaboration actually looks like. So that's function applications. Bindings, they're not really any more complicated. So you've got something of this form, x of type s goes to t. Well, we better check that we're looking for a type. If we're not looking for a type, then a function type is not going to work. So we'll tell it it's a type. Then we'll invent a hole for s. So s had better be a type as well. So we claim that s has type. I kind of glossed over the universe hierarchy as well here. So type actually has type 1. Type 1 has type 2. What really happens internally is that we work out the constraints between the universe levels and then feed them off to a solver that looks for cycles. We have cumulative universes, if that means anything to you. If not, don't worry. I don't want to go into it here. We've invented some whole s. And then we'll make a binder, x of type s. And the next thing to do is just elaborate s and t recursively, and we'll hopefully get a valid type. So to build this application, just claim some s in type, make the binder, focus on that type and elaborate nat, and then, well, the next hole is going to be the scope of the binding, so let's just elaborate it. So there are, once we've elaborated terms, we're going to have to elaborate declarations. So we have sort of 2 levels here. We have terms which are just TT values, and then we have programs which are sort of pattern matching definitions, data declarations. So elab is the monad that builds terms. Run elab, well, this is an outer monad called Idris. This is the kitchen sink, everything that we need to elaborate programs monad. So to run the elaborator, we give it a name and some type. So this starts up the type-directed elaboration process. We give it a tactic. So this tactic is probably going to be some giant tactic that describes the entire program. And if we're lucky, that'll come out with something in our outer monad. So you'll notice that elaboration is type-directed. We've got an Idris monad that encapsulates all of the states that we have in the system. Oh yeah, I should draw attention to this pattern argument, because things are slightly different depending on whether we're on the left-hand side or the right-hand side of a pattern match. On the left-hand side of a pattern match, we might be introducing new names. So there's going to be pattern variables, so we're going to have to know that we treat them specially. On the right-hand side of a pattern match, we're not allowed to introduce new names. We're only allowed to use names that we've already got. So this pattern argument just says how to deal with names that we haven't come across yet. So yeah, on the left-hand side, just make a pattern binding. So, for top-level declarations, everything has got to be of this form, a function type, an application. So to run that, we'll elaborate the type, add f to the context. Once we've got f in the context, we can elaborate the left-hand side, and any out-of-scope names, we'll just assume they're pattern variables. There's a little bit of a difficulty here, actually. You might wonder how, on the left-hand side, we can be type-directed, since we can't possibly... We know the type of f, but we don't know the type of f and its application. So we actually do a little bit of a cheat here. I have a data type called infer, which takes two arguments, a type and a thing. So so we're actually, the type-directed elaboration we're doing here is to generate something of type infer, and the hope is that this will be simple enough that when we elaborate it, we can fill in the type argument. If you can't do that, well, you have a problem. It's unlikely that this is going to be a problem because we've given the type for f, so we should have enough information. Then on the right-hand side, we just use the type that we inferred for the left-hand side and check that they're the same. So all we're doing here is just calling the elaborator for the left-hand side for the right-hand side. It's simply a case of elaborating each term in its own context. Nicola?
Is it only variables on the left?
No, there could be patterns of any kind of.
There is several.
There are several of these things. Functions with where blocks get a bit more awkward because where blocks aren't allowed in TT, so we'll have to think about how to deal with that. So what do? Well, elaborate the left-hand side of f just as before. That gives us all the pattern variables. So that tells us everything that is going to be in scope when we elaborate the where block. So now we have all the information. We just sort of need to seed the elaborator with that information. So we'll lift those auxiliary definitions, so f aux and any others you might have, to the top level, just adding the pattern variables from the left-hand side in the order that we need to have them in order to maintain them type correctness. And then we elaborate those auxiliary definitions and elaborate the right-hand side of f like normal. So all we're really doing is lifting this out to the top level before we type check it. There's quite a lot of annoying code there to deal with, name shadowing in the where block and inventing appropriate names for this auxiliary definition. But really, all you're doing is adding the arguments and elaborating as normal. So type classes, I'll show you how they work. Again, you have to work out how to turn them into data declarations and top-level function declarations. So given a type class like this, well, really this is just a record containing whatever the show function is. And then this instance is defining a specific show function. So that translates more or less directly into this data declaration and function. So the type class becomes a data type. It's a record containing one function show, so you've got to give it a name. And then the top-level show function. This is a mistake. This 0 greater than. This should be a minus greater than. It's quite hard to cut and paste this stuff because it looks really ugly when it comes out of the system. We've got a top-level function that when you call show, this is just the function you call. And then the instance is just making a record from the definition that you gave it. So this definition here just gets copied into a definition here, but just pretty much directly textually copying. That's all there is to it, really. So actually, type class arguments they're implicit arguments too. They're just a special kind of implicit argument. Most implicit arguments will be solved by unification, but type class constraints are going to be solved by a type class resolution procedure. And surprise, surprise, it's a tactic. So we've got a hole that we need to solve somehow. We haven't got a program for it, but we do have some information in the context. We know what type it's supposed to be. And given that type classes are data structures, and given that there should only be one instance of that data structure, all we have to do is look for something anywhere that has the right type. And then if we find something that has the right type, well, we've won. So it starts just by looking for a local solution. Like if there is a type class parameter being passed to your function, it just uses that. If it can't find that, it's going to look for globally defined instances. And finding a global type class instance might lead to more constraints. So, for example, you've got ord is derived from eq, so you might have something you need to chase there. Or show of list of A depends on show of A, so you'll find show of the list, but then you'll have to carry on searching. So that might give rise to further constraints, but you just solve them recursively. So this is a really simple way of resolving type classes. But it gives you basically gives you Haskell 98 style plus multiple parameters. Right, so that's elaboration. I spent a bit longer than I expected to talking about elaboration, but if you can cope for another 10 minutes, then I'll tell you a little bit about the compilation problem and how we tackle it. So I see this kind of. Is everyone happy with elaboration? Did that sort of, it seems reasonable. Good. So this sort of comment is something I see occasionally on various online forums, IRC channels. I occasionally hear it when I'm talking to people at conferences. I don't remember who said this. They probably don't want me to say it anyway. And it's unfortunate that I picked this one because there's lots of others times that this is said. So there are also all kinds of issues with the complexity and performance of compiling languages that have dependent types. And every time I see that, I think, somebody should write a PhD thesis about that. I did, by the way. So this is what my PhD was about. And clearly, I'm doing something wrong if people aren't aware of this. So my instinctive reaction to this. I'm not being totally fair here. There are also all kinds of issues, is what this person said. There is one issue, which is not all kinds of. It's just one issue. And the issue really is type erasure. We've blurred the distinction between terms and types. We could have values go in types, types go in programs, we compute types. So it's not obvious that there's a distinction. So people often talk of the phase distinction between types and values. In fact, I went to Wikipedia, which, as you remember, is the definitive source of all knowledge. And and Wikipedia said the phase distinction, yes, that's the distinction between types and values and how they're different. Well, I think the key word there is phase. What could phase mean? Well, phase means the point of execution, or the point in the program's lifetime. We have a compilation phase, we have a runtime phase. We don't have a type phase and a value phase. They are kind of syntactic parts of the program. But conventionally still, it's seen as a separation of types and terms. So, before executing a program, you erase the types, and there is this perceived complexity that you can't tell exactly what the types are. So we'll have to think we can't just erase them. But yes, it's really a separation of compile time and runtime. And what we're going to do is, rather than erasing types before running a program, we are going to identify the compile time parts and erase those, which might be values, they might be types, whatever. So obviously that distinction is rather harder to make. Conventionally, you can just look at anything after the colon in the typing judgment and say, right, that's gone. Bit more to it than that with dependent types, because as you've seen with these implicit arguments, and you've seen with the definition of lists earlier, we had the type as part of the term, we had the length as part of the term. I think, well, clearly these shouldn't be necessary when we're running the program. How do we identify which of these are necessary? So Idris achieves this by, looking for any value that it can prove is unused, and it doesn't go as far as it could at the moment, but it does go quite a long way. It certainly, as far as I know, it goes further than any other dependently typed language. So it will either erase values which are forced. So forcing is a forced argument is a constructor argument which can be determined exactly by that constructor's indices. So in the case of nil, for example, you can tell what the type is just by looking at the index of the vector. Now, you know that this is going to be okay because that type is going to be in scope somewhere. It's basically duplicated. Also, collapsing. So collapsing, a collapsible data type is a data type that provably only has one inhabitant. Now, this does rely on totality checking, because if you don't do totality checking, then every data type has at least one inhabitant called bottom and the other inhabitants. So you need to do a totality check to make sure that bottom is unavailable to you. So typically, what collapsing will erase is equality proofs, predicates, anything that you've written down to prove some property of your program, rather than to be the program itself. So we're looking for non-computational things. Then once we've done that, the result of forcing and collapsing is typically going to be to remove stuff. So removing stuff is going to have an effect. There's going to be more static analysis we can do after that. So after we've done that, we can erase any kind of function and constructor arguments that are still not used. We can say, well, these were only used in positions where we were never going to inspect them, so we can totally erase them from the program. So I'll show you an example of that. Let's go back to good old vectors. I always demonstrate things with vectors, because although vectors aren't exactly every dependent type, they are an easy one to understand. So here's vectors in TT. So we've got this A, I've got this A and this K, and you can see in the indices of nil, you've got A is 0. So by pattern matching on this A, we can work out what this A has to be. And by pattern matching on this successor of K in the cons case, we can work out what K has to be. So given that we can pattern match on the indices, rather than pattern matching on the constructor, we just chuck them away. So we can erase this A, and this K. And we've got a program down here. This is our VAD that we had earlier. I've taken away the pattern bindings just because there was too much noise. So this is VAD without pattern bindings. We're going to erase this A, this K, and this A and this K, and so on. So just throughout, we're going to chuck them away, and we get that. So nil doesn't take any parameters anymore, and cons only takes the head and the tail. Now, if you look in VAdd, so you might worry. So I said, we say we can chuck away anything that's in the indices. You might think, well, that's in the type, so surely that's a problem because it's in the type. Well, because it's in the type, it's also going to be, it's in the type of vect, it's also going to be an argument to any function that uses a vect. So we do actually still have it, but now we only have it in one place, whereas before we had it in at least one place. So this recursive call to VAdd takes the A and the K from the types, but it's okay, we still have the A and the K because they were implicit arguments to VAdd. Still, there's a bit further we can go here, because you will notice that in this clause, this first clause, A is never used. And you'll notice in this second clause, A is only used in this recursive position, and K is only used in this recursive position. So what's going to happen is we eventually get to the base case, and we haven't used it. So why not just get rid of it? So we'll just blot out these arguments, and on the right-hand side, anytime we call VAdd, we just replace it with some blob. This is actually compiled to null. So we're sure it's not going to be inspected, so we just chuck it away. Yes, question?
So how did you decide that you don't use the K?
It could equally be pattern matching on number and then on the vector.
Yeah, but, yes, good question. Why would it do that, though? Because we already have enough information to do the pattern matching on the other arguments. So effectively what's happened here is the only way you're ever going to use the K is to do a match distinction that you already knew how to do from something else. Or, and that's always going to happen. Because you've got different constructors, there's different information there. What the compiler actually does is it looks at the possible case trees that it could build and makes sure this is impossible. I don't want to go into the details of how that happens, but it's actually more tricky than I've made it out to be, but not much. It's just a little bit annoying. So yes, you can safely erase that because certainly in this case, that there's nowhere where you can look at it. Now that was forcing. We've actually ended up with the program we first wrote, which is quite pleasing. We've done an awful lot of work to get back to where we started, but we know that we've got back to something that is valid, that is correct. This is why this is a good thing to do. We could have just written this in the first place, but we wouldn't be able to get it through the type checker. So collapsing is a step further from this. So this is a collapsible data type. It's the less than or equal predicate on two natural numbers. I said less than. I mean less than or equal. So 0 is less than anything, and if we know that n is less than m, then we also know that n plus 1 is less than n plus 1. Now, there is no computational content in this. You can tell everything you need to know about this data type just by looking at the indices. How can you do that? Well, I'll show you. Here's a program that uses it. So we've got a minus function that, given an x and a y, and a proof that y is less than or equal to x, so it's now a safe minus. It has to be a minus that actually leads to some answer. So x minus 0, provided we've got some proof that that was an okay thing to do, is x. And x minus y, provided we've got a proof that that is an okay thing to do, is so suck of x minus suck of y is the same as x minus y. But we have to push this proof through and manage it recursively to show that it's a valid, minus is a valid program to write. So let's do the same analysis on less than or equal as we did on vectors. You'll notice that this m is in the type, so we're okay. This n and this m, they're both in the type, so they can go away. So we've got this. That's the result of the forcing analysis. So this argument's gone here, it's gone here. So all we have is the end and then something, the step case. This is actually looking suspiciously like just a natural number now, actually, isn't it? It's a 0 and a successor. This is going to be equivalent to whatever n is. So however many successor symbol n has, we're going to have that many LTS constructors. So notice that all we have is this recursive argument and these indices. Now, we can tell exactly which. So this correspondence with successor is important. We can tell which of these two constructors it's going to be, not by looking at these constructors, but by looking at this constructor on the index, on the first argument to LE. So if it's a 0, it's going to have to be LT0. If it's a successor, it's going to have to be LT successor. So we don't need to distinguish between the constructors. All we're now left with is this recursive argument. And we know, just like our analysis on the add, we know that after we finish following this recursive argument, what we're going to get to is finish, the end. So there's no information left in this data type. Everything we had available was something we could get from somewhere else. So we just chuck the whole thing away. Anytime we see either LT0 or LTS, just chuck it away. So minus now, this is the program you would have written, but you've thrown away the proof that it was valid to do it. You know that it's valid to do it because, there's no other way. When you type check the program, there's no other way that this could ever have been written, so you don't need to bother checking anymore. You don't need to check at runtime. So that's collapsing. So that's all about phase distinctions, and this is basically the end. I have just a couple of things left to say. So, any more questions on compiling before I'll maybe tell you in a bit more detail about how that final erasure works, because if you get around to running your Agda programs, it might be useful. So.
I mean, the ethics pattern.
Yeah.
Very similar.
Sure. Yeah. So I know it does forcing. I don't know if it goes as far as collapsing.
No, it doesn't do collapsing.
Yeah. The trick, by the way, is to translate case analysis if there's only one possibility to direct argument projection. And if you do a direct argument projection, you can do the same thing. So basically, the case trees have gone away. Anyway, I'll tell you about a couple of undocumented things. And the reason I tell you about these undocumented things is not because this is me documenting them, but because you can use these to get some kind of idea of what's going on inside the system, what programs actually look like when compiled to TT. So there's a command at the REPL called DI, stands for debug info. That normally that does whatever I'm currently working on at the minute. Gives you a dump of what's happening. Typically, it gives you, so you give it a name as a parameter, and it tells you all the internal details you never wanted to know about a function or a data type. So it tells you in particular whether arguments are forcible or collapsible and which arguments are erasable. So it gives you an idea of what the program actually is that you're compiling. It's also a logging directive. So logging is, %logging is something you can put in your source file. And from that point on, the elaborator will just spit out loads of information about what it's up to. And this means that you can see exactly what the left-hand side of a pattern match looks like, what the right-hand side looks like. I use this for debugging purposes naturally. So what this gives you is typically, you get an idea of which bugs I've had to fix actually by looking at what the output of logging is. Also, the dump case is compiler flag. So this takes a file name as a parameter, and this will give you an output of the case trees that actually get compiled. It tells you the program that you're actually running. You can see which things have been erased, for example. You can see what the case trees look like, so what it was actually pattern matching on, and so on. So as one additional exercise, if you feel like it, so take the exercises you've done already. So you see there aren't any exercises I've specifically given for today, but as an additional one, if you have got through everything and you're a bit bored, it could be instructive to use these features just to see what the internal representations of the programs you've written actually turned out to be. It does take a lot of practice to work out how to read them. The only reason I know how to read them is that every time I've added a logging, I've specifically been looking for something. And I tend to keep things in. There's no point I find it useful to keep them in. Right, so that's pretty much it. I'll just remind you what we've done. And so you know what you've learned. So I've talked a bit about just programming with dependent types, just the basics of theorem proving, writing predicates, what it means to be a dependently typed program. And then as applications, so it's for a long time we kind of felt that dependent types were a solution looking for a problem. It's very cool to be able to prove things correct about your programs, but the question is, who cares? Well, I'm trying to say that you should care if you're interested in extra functional correctness, resource properties of your programs. So this is something that very much interests me, and this is what I've tried to get across to you, that dependent types can be used for that kind of resource tracking problem. Also, something more kind of practical. Managing side effects is something that I found particularly annoying when programming in Haskell. So I thought, well, can we use the power of dependent types to do something about that? So this is what we saw yesterday, basically using dependent types to make more generic libraries, more expressive libraries. Even if you're not writing programs with dependent types, you can take the power that the type systems give you to write libraries which are more usable for real application programmers. And then finally today, I've given you an overview of what's happening inside Idris. So if you want to get involved in the project, you hopefully have some vague idea of what the structure of the code is, what the features you need to worry about are. So clearly there's a lot to do. This is a fairly young language, and it's certainly a research project, so there's plenty of research problems to tackle. I just picked a few that occurred to me while I was writing this. So Haskell has this deriving feature for type classes, which is I wouldn't be without. Unfortunately, when programming in Idris, I am without it. And Haskell, the Haskell standard defines it, says you have to have it for certain type classes, show, eq, ord, and so on. And people occasionally add more, so functor is derivable now, and there's a template Haskell library that does all kinds of exciting things, binary. I don't want to hard code deriving for particular type classes, though. I would quite like to work out how to do it nicely, properly, generically. And I haven't worked out how to do that. I've seen solutions for Haskell, and while they work, I just don't really like them. They're just sort of noisy. So I'd like, if someone wants to think about how to do that nicely, that would be, I'd love to see how to do that. So runtime data representation is another thing. So I said the other day that it was possible to compile NATs to a sensible machine representation. I haven't implemented that yet in this version, and the reason I haven't is, again, I don't want to hard code it for just one data type. So can we find a way of doing it for natural numbers as well as vect. So a vector of a certain size, you know how much memory you need to allocate. Is there a nice generic way of writing down how to do that machine translation? So decisions procedures would be nice. Can you write a Presburger arithmetic solver that can do n plus m equals m plus n automatically? Is there a framework for? Can we make a framework for building that in nicely? One final thing that would be really nice would be just more tools for supporting programming. The most obvious thing is type-directed editing. So this is something I'm very jealous of in AGDA, is the type-directed editing you get through their Emacs mode. So I'd like something like that, but I'd like it to be more generic and not tied to a particular editor. I don't want it to work by generating Emacs Lisp, for example. So it'd be nice to have something like that. And something else that David mentioned this morning, so it was coincidental that I'd already suggested this, is something like Hoogle would be fantastic. But just Hoogle is going to be probably not enough. I think there's a lot more to it when the types are potentially quite complex. So I'm even keeping a list of these things on the web. So on the website, there's a help required page that you can take a look at. And I try to keep it up to date. So there's things I think of, I tend to stick it on there. And so if there's anything there that interests you, it's all the things that I have no intention of doing myself in any reasonable time. So you won't be stepping on my toes certainly by doing any of them. Okay, well that's all. Documentation on the web. Do feel free to join the mailing list. Ask any questions on there. So there's quite a few people on there who will be able to answer questions, and also quite an active IRC channel on Freenode. So if you have any questions or have any interest, then do feel free to join us. But yes, okay, I think we shall stop there. And it's time for some coffee and more hacking.